Yeah, here we are once again at the physics video lecture. This is fluid mechanics video lecture 11. And we may be wrapping things up today, although there's quite a few things to talk about. So we had Navier-Stokes equation finally, and we had solutions of channel flow. And what I'm going to do is set up some other problems and discuss them kind of in generalities, as it were. So we have our Navier-Stokes equation. That is the Euler equation with the friction term added. So that is very familiar to us now. Minus 1 over rho. Gradient P will say we, that external field would be inside the pressure if we want. Just keep it simple. Plus, now we have eta over rho del squared V. And the first thing I'm going to introduce is define the letter nu as this eta divided by rho. And also, strictly speaking, under these circumstances, we have assumed constant density. So note right here, density is constant, because if density is not constant, you actually have more, you have a second viscosity term as well. Okay. So this is the case that is of most interest, and let's just mention the solutions that we have, and then I'll mention some solutions I have in my notes that we're not going to do, but they're also important. So the first solution was the channel flow. And the thing about it is that you get the parabolic velocity profile. So the flow speed is greatest in the middle, parabolic down to 0. Maybe I should draw my parabola first, right? But yeah, and of course the velocity vanishes at the fixed surface. So we have the channel flow, and that was an exact solution, so that's a very important one. And it's got the parabolic flow, velocity flow, and the other flow is the pipe with a circular cross section, and it too has the same type of parabolic flow here. You can make a better parabola if you try. Okay, you put a parabola in here, and then the rest. So pipe flow, channel flow, both of these have parabolic velocity profiles. And of course, when you take the curl, you find that they have vorticity throughout, except right down the center. Parabolic velocity profile, and I'll just write vorticity. Curl of V is generally not equal to 0. Now another flow that one can get an exact solution for is flow between concentric cylinders. And not only between concentric cylinders, between concentric rotating cylinders. Concentric rotating cylinders. Interesting experiments done with those. I'll say why later, but this would also be, let's mark these down. These two were exact, but they're not all going to be exact. So these we did, they are exact. And this one here is also exact. The flow between rotating concentric cylinders, right? You can imagine you have these two concentric cylinders here, and not only are they filled with fluid, but they're rotating. They can be counter-rotating, they can be doing a lot of things. So flow between concentric rotating cylinders. Also exact. For these, you have to go to differential operators in the say cylindrical coordinates. A bit of work to get these. Okay. So another really important one is the Stokes flow. That is just the flow past a sphere. Okay. And you can change your point of reference, and you can say you have a sphere that is falling through, say moving through a fluid, or you can imagine the sphere in one place and the fluid flowing past it. So that is called Stokes flow. Flow past a sphere. I'll just say sphere radius r, and it's already interesting here because I introduced earlier on that the force F is equal to 6 pi eta VR. Right, that's the force, and of course it depends on the viscosity. And in the full semester course, we actually did this. It's a major project to get this result here. It's not enough to know the Navier-Stokes equation. You actually have to have the stress tensor so you can actually get the friction contributions. Okay, so let's even draw a little picture here. So you've got the sphere here of radius r, and you've got some flow around it. Actually, it's a major project. Okay, just to have a visual here. It's a major project to get the flow and then get the force, which is another project on it. It's an important one. This is used in the Millikan experiment. It's used in the original Einstein determination of the size of atoms, Brownian motion, that type of thing. Made use of this result. Okay, so it's an important one. Is the Stokes flow an exact solution? It is not, because it's solved under the assumption that the speeds are slow and you can drop this quadratic term. So its solution of -1 over rho gradient P plus eta over rho del squared V equals 0. Okay. It's because it is a, what do you call it, a steady state flow, so this is gone and these are considered small. Okay. Assume V dot grad V is small. Okay. Nonlinear terms. We've done that before. So even this and this is also in the full semester course. We actually go through all the steps to get this and do this calculation. But nonetheless, it is not an exact solution. So not an exact solution. So the exact solutions are far and in between. Something we did, maybe I'll bring up, we did the waves on the surface of a fluid. That's actually an interesting thing, because for the waves on the surface of a fluid, we didn't have viscosity, so we said we had the potential equation, but then we ditched these second order terms because they're small. And in my notes, I also have the waves on the surface of a fluid, the gravity waves, including the viscosity. And you get pretty much what you'd expect, although there's some interesting aspects of that. You get damped waves, okay? But again, it can't be considered an exact solution because we're throwing away the nonlinear terms there. So important, but not exact. So let's keep going. I'm going to keep the equation up. And I'll keep the numbering going, so that was 4. So 5. The fifth one I want to bring into play a problem that is not, and pretty much the same picture as this, the potential flow past a cylinder. Now the potential flow past a cylinder, of course, is not Navier-Stokes. Okay? It doesn't have the dissipation term here. But we're going to talk about potential flow. We talked about it before. We could have actually derived the exact solution, not that difficult to do. I think I'll put it as a homework for you guys to look it up. Look it up and put it in your notes. As a cylinder, so that's a 2-dimensional potential flow, and it's the same picture. You've got a cylinder here of radius r, and you're looking at fluid flow past it. Now the interesting thing here is this is an exact solution of Euler's equation. Solution of Euler's equation. And what's Euler's equation? It's the Navier-Stokes equation without the dissipation, but it has the different and the wrong boundary conditions. Okay. So if you look up the exact solution, or calculate it, look it up, what you'll find is if there's a speed here, I'll say speed u at infinity, right? Those speeds are the same at infinity. We talked about how the symmetry of the situation leads to having the same pressure on the right side as the left, and you have the paradox of there being no resistance at all. Okay, so if you have this speed at infinity, what you find is you're actually going across the surface here with double the speed that it has at infinity, a complete violation of the boundary conditions which state that, so the physical boundary conditions that go with this term here that state that the velocity vanishes. Okay, so this solution gets a lot of attention, but is very problematic in terms of reality. But you know, people can't resist it because it's exact and it's actually kind of beautiful. So go ahead and look this up. I'll even write that down as homework. Today I'm going to give you a number of things to look up and get screenshots and post them in your final notes. Okay, so homework. Look this up. Look it up. Include images. There's really nice images of these flow patterns that you can find better than you can draw. And you just take a screenshot on the computer, print it out, and turn it in with your notes. Okay. So yeah, this is a good thing to talk about. So this is something that one would really want to have an exact solution to. Okay. And I'll explain why in a moment. Okay. But yeah, that's a little list of some interesting flows. In particular, the kind of flow past an obstacle. The reason is this, and it actually holds true for the flow past the little sphere. The reason is this: you don't have this smooth pattern except at the beginning when the flow speeds are small. When the flow speeds increase, there are little developments, eddies form, and all kinds of complexity emerges. And it's ubiquitous in nature, and one would actually want to understand it better. What is done is a lot of numerical simulations of this. I'm going to also ask you to get some pictures of some numerical simulations that you can include in your notes as well. But we'll come back to that. At this point, having said how hard it is to solve this, what I want to do is rescale the Navier-Stokes equation and show that how it can be used to get information anyway. So let's leave this up here, and our next topic is rescaling the Navier-Stokes equation. This is a major industry, so to speak, and we'll just do the most basic rescaling of the equation. And I'll start with a picture like this again. So our next topic, rescaling the Navier-Stokes equation. Yeah, so the picture we have in front of us is again that we have a flow, and I'm just going to characterize the size of the object by L. It doesn't have to be a cylinder, it's just an object characterized by the length scale L, and we have fluid flow around it, and out here at minus infinity we have speed at minus infinity, and then same thing. So we're going to have a characteristic speed. Characteristic flow speed. Okay. So now let's, when we say rescaling, we want to have dimensionless quantities. Dimensionless quantities. So what we do is we're going to introduce V star is equal to V divided by U, right? This is the characteristic speed. This is the actual velocity field. So you divide V by that speed, and you have a dimensionless quantity here. And we'll also introduce IS, the length, R, or the position type of angle length, R star would be R divided by L, right? So we've got U and we've got L there. And T star, this one can be done differently. There are different rescaling schemes out there, but we're going to do the simplest one. And T star would be T divided by a time, and we can make that L divided by U, okay? Because a length and U is a length per time, and so time over time. Okay. So we're going to rescale things like this, and now let's do that. So dV dt is going to be, there's a star there, d dt of U times V star, because that's what the V is going to be. So U times V star. And U is just a constant, so we pull it out. And then we've got d V star d, and then our T is L over U times T star. So I'm just going to write L over U T star. Oops, star goes in the bottom there. And this too is just a constant. So we pull that out and then invert it, we'll have U squared over L times dB star dt star. So that's the first term. Okay. Now for V dot grad V, we're going to write it this way. V d dr V. Okay, I'm not worried about the actual collection, I'm just worried about the dimensions here. So we can do that. V d over dr V. And that will allow us to write, for V we have U V star, and we have it twice. So we're going to pull out U squared, and then we'll have V star D, D, and then that R is going to be L R star, so L R star and V star. And you can see what we have. We again have U squared over L. U squared over L. And now we have V dot grad V. I'll revert to that. And everything gets a star. Okay. Now the gradient of P is going to be a little bit different. Now minus 1 over rho gradient of P when we take the gradient star, so that's minus 1 over rho d d L R. Okay, that's going to be the gradient star, L times R of P. We only get minus 1 over rho. We get L out here. And so this one I'm going to define gradient star P star by putting in a U squared by hand. Okay. So U squared. So here we have, in addition to these conventions here, we have P star is equal to U squared P. Other way around. P is equal to U squared P star. So P star is P over U squared. And that would cancel that one because I put it in by hand. Okay. So yeah, this one we have to include here with these rescalings. And yeah, you're rescaling the pressure just by another constant, okay, which happens to be part of the problem. Finally, I have room on this board. We need this last one. So the eta over rho, which we're already going to call nu. So nu del squared V, going to have nu, and this we're again going to write d squared d L R star squared, and then U V star, okay, U V star. And so what we have here is nu. This is squared. We have nu times U over L squared, and then we can write gradient star squared V star. Okay, so all of the ingredients are in place. We're going to write it all out once with the stars, and then we'll drop them, but first we gotta write the whole thing down. Okay, let's go ahead and leave this up and work right underneath here. What we're going to do is, we can even start with the first one. We have all four of these terms now from this equation, 1, 2, 3, 4. We're going to multiply them all by L over U squared, which is going to cancel that dimensional quantity, right? So we're going to multiply them all by L over U squared. Okay. Multiply by L over U squared. And what we get is D star, T star plus V dot grad V, stars everywhere, okay, because they're rescaled, minus 1 over rho gradient star P star. This one we had to do that little thing there. And what we're left with for the last one I'm going to write out, we have L over U squared nu U over L squared. V star. Okay. So the punchline is here. Hopefully I got this right. So what do we have here? We can cancel one of the L's and the U. Yeah, this is good. What we have here is nu over U times L. And this is the inverse of the Reynolds number, equals RE to the minus 1, where RE is equal to the inverse, UL over nu is the Reynolds number. So having done all that, we know what we did. We made the whole equation dimensionless. We made it dimensionless, and we rescaled it. So what is that good for? Let's go ahead and write this down once more. In fact, we can now drop the stars. Okay, so after rescaling, but yeah, you want to showcase both of these. So after rescaling, we have, simply because we don't want to write all these stars, but it's understood what we did here. V dot grad V minus 1 over rho gradient P plus Reynolds number to the minus 1 del squared V. Well, a little close there. Okay. Less than beautiful. You guys make this nicer in your notes. I may actually rewrite it. So what do we have here? This is visible enough, right? We've got this Reynolds number to the minus 1. So the Reynolds number goes towards infinity when the viscosity goes towards 0. Okay. And of course it goes to infinity if the dimensions and the speeds grow. But what we say is, in the limit as the Reynolds number goes to infinity, we would get back the Euler equation. Okay. But this combination is universal in the following sense. Suppose we go back to a flow pattern like this here, then as long as the Reynolds number is the same, we would have the exact same mathematics. Okay, so we would have a universal flow pattern as long as this combination, this speed, this dimension, this viscosity, give us that same number, Reynolds number. So this is used, even though you can't solve this differential equation, you can rescale things and you can build, for example, wind tunnels. Okay, you can do a small scale version of a large scale object, airplanes and stuff, wings, and then study their behavior study the behavior with a small scale model, of a larger object. So it's very, very useful to be able to rescale these equations. And if you do the more general equations, including temperature and frequencies and other things, then there's a whole list of these numbers that allow you to rescale your systems. Okay. So that is very important. And we did this systematically. There are other schemes for that. For example, instead of just scaling the time in terms of L and U here from our picture, you can bring in an independent time scale if you're talking about an oscillating system, okay? Then you have an independent time scale based on a frequency, okay? So that kind of thing can be done as well. But this is a good version of the whole thing. Again, when the Reynolds number goes to infinity, remember it's in the denominator here, so when it goes to infinity, it makes this thing here smaller. Okay, I'm going to keep working with that picture. So again, even though you can't solve this differential equation, you can say two flows are dynamically equivalent if they have the same Reynolds number. And of course, you'd have to deal with the pressure as well. So again, I dropped all the stars here, but we said after rescaling, maybe I should write drop the star. Okay. And then you get this. Again, it's a Navier-Stokes equation. Yeah. So that's the point. Maybe I'll write that down. Dynamically equivalent if they have the same Reynolds number. Number. That being said, in some subsequent discussions, we'll just go back to using this form of the equation, but it's important to have seen this done. I'm going to consult the clock. Okay, great. So yeah, and wind tunnels, kind of thing you could look into, very interesting. Wind tunnels, etc. Okay. And basic scaling, you could scale boats in a movie scene, for instance. You'd want to, yeah. So basic scaling. Okay. I wanted to go back to this scenario here. Flow past an obstacle. And this time we're talking about a real flow, so let's let it be a cylinder. certain size. But yeah, we have this flow here. And as you increase the Reynolds number, which is to say, as you increase the speed, or whatever else you do here, but as you increase, and we can just say increase the flow speed, so we can have the same obstacle and we're just dialing in a higher and higher flow speed. Instabilities will develop. So at a slow enough speed, you have this smooth flow. At a certain point, you start developing these little eddies here. And at first, you just develop them close at hand. So yeah, make sure this is the solid object. And these eddies will detach and flow downstream. This can be simulated numerically, so we know that the Navier-Stokes equations will deliver that, but we can't actually get an analytic solution to that, and that's an important problem. So formation of eddies as the flow speed increases, and more generally as the Reynolds number increases. So the fully developed picture here, actually if you were to keep increasing the flow speed, these would become larger and then they detach and flow downstream. You keep increasing it, serious turbulence would develop behind this thing. So there's a progression. You go, so well, it's right here. There's a progression that goes like this. You'd have smooth flow, and then you get the formation of these structures. Eddies form, little vortices, and then these eddies detach and are carried downstream. Flow downstream. And things get rougher and more complicated, and eventually you have turbulence. And then you would, in that highly developed turbulence, you'd have smooth flow in front, and downstream behind that object, you just have a totally turbulent wake, it's called. So all of these things one would like to actually calculate, and these are unsolved problems. Okay. Unsolved, partially solved. And they occur at all different scales, right? You go back to your Reynolds number, you see you can have any number of different scales. These type of phenomena occur in a laboratory, in a tank. They occur actually in very, very small volumes of water. If you're dropping a little ball bearing, say, through some fluid, these kind of things are going to happen. They happen on a planetary size in the weather. They happen in accretion disks of related things, of stars. So they happen on every scale, and there's still a problem that people want to have the answer to. So that's one of the reasons I'm definitely wanting to leave you with these things. Now, another thing you can look up, this is a rough description of what's called the von Karman vortex stream. So homework here, you also want to look up and get images of the von Karman, a great fluid dynamicist. Von Karman vortex stream is what it's called. And here's what I want you to do. You want to get images of computer simulations. You want to get images of smaller and larger scale. For example, these things will form downstream of some island in the Pacific when there's a wind and clouds blowing by it, okay? So von Karman vortex street, so we want images for simulations, lab, and in nature. If you haven't seen them before, you'll be amazed. Okay. You'll be amazed. Okay. So the last thing I'm going to talk about, and you know, I think I'm going to consult the clock. I think we're going to be able to wrap this up. Yeah, by getting these images, you'll have some things to look forward to. A lot of people have tried to solve these types of problems, and they're still outstanding, still needed. So yeah, so what we go to from here is the idea of the instability. Okay. So this progression right here, smooth flow, eddies form, this is an example of an instability because the equations of motion, remember when we solve the equations of motion, say this equation, it's the easiest one to look at, okay, this one up here, but that's the same as this one right here. When we get the solution, we're always getting the version where the flow is steady state and this explicit time derivative vanishes, okay? So we would be solving this part of the equation right here and trying to get a flow field. And then there's really no reason for this flow field not to exist for arbitrary speeds. Okay. But of course, in reality, it doesn't exist for arbitrary speeds, but these eddies and things form, so that tells us that the system is dynamically unstable. So that's what I'm going to talk about next. Okay, so some of these we're going to rewrite, but I'll clear this board first. So the problem is actually very well defined. We've got the equations of motion, we have the idea of a steady state flow, and you know, we have empirically these progressions from steady state to instability. So let's have a look at why this is, although well defined, why it's so difficult to work on. So this last topic is instability. Of fluid flows. And I'll give two examples. First one would be the pipe flow. And by the way, you can get good pictures of these as well, good images. So the first example is the pipe flow. And the second example is the flow around an obstacle. Okay, so what about the pipe flow? Let's just draw our famous profile here. So we've got this velocity profile. Fastness in the middle, vanishes at the boundaries there. So what happens if you increase the speed of a pipe flow? Well, we had the exact solution, and nothing happened when we increased the speed, okay? We could have a speed really just dependent on the pressure gradient, okay? In reality, and you can get some good I've seen some good videos of laboratory work where they have a pipe that's clear and they send a dye. They send a dye right down the middle, so it has this thin red line, let's say, right down the middle, and as they increase the flow speed, at some point this little red line starts to wobble, and they keep increasing it, it just breaks up. It breaks up and you actually get turbulence downstream. So again, our solution didn't say anything about that, but there's this progression, and maybe we should put a couple of words here. So this is a line of dye. Wobbles and breaks up. I'll just call it that. Wobbles and breaks up as the flow speed increases. So you guys look one of these up. That's pretty interesting. As speed increases. And check your notes. We have the solution to this. It's just the pressure gradient increases the speed, and then that thing, that smooth line of dye eventually wobbles and breaks up. Okay. So that is an instability. And of course, the flow around an obstacle is what I had just been talking about. Okay. So there's our obstacle. Flow goes around. Increase the speed on it, and eventually you start to get these eddies forming, and you're going to be really impressed to see those. Okay. So again, that too is an instability, and the question is, how do you deal with it mathematically? And so, by the way, this is lab work, and in numerical simulations, these things can also be demonstrated using the Navier-Stokes. But I'll just do this last derivation for linear stability analysis. And we'll see why it's in principle doable and in practice very difficult. Which just means it's waiting for someone to tackle it and figure it out. So this last thing, I got to consult the clock once more. Yeah, we'll do this right now. So this last thing is called linear stability analysis. Stability analysis. So what we're going to do is take a steady state solution. So here's what we have. We have, first of all, the Navier-Stokes equation, and we'll just write it out with the viscosity, gradient B, what do we have, nu, oops, not eta, nu del squared V, and you guys remember nu is equal to 8 over rho. So that's the first thing. We want to solve this for a steady state. So to solve for a steady state, which is to say you have a steady flow, so that first term is 0, and you call the solution V equals V0 of x, y, z. So the solution is not a function explicitly of time, right? And then what you want to do is expand around there. So what we want to do is find a perturbation. So this is the time independent. So then let v of x, y, z, and t be equal to this v0 that we supposedly found. Actually, we did find a couple of them. We found our channel flows, right? And we could find one or two more. So v0 of just position plus v1 of position and time. These are all vectors. And v1 is small. So, because v1 is small and we're going to linearize. Where v1 is small. And then we have to linearize the Navier-Stokes equation. And I'm just going to do that. I'm just going to write the whole thing out. It's not that bad. You've got these two. This is your steady state. This is v1. You want to linearize it and find out, does v1 grow? Okay. Actually, I'll state that criterion now. Does v1 of r and t grow? Question mark. Then we say the steady flow is unstable. If v1 decays, then we would say it's stable. So this would be a little perturbation. Does it just go away or does it grow? Then unstable. Then the flow is unstable. Does v1 decay? Then the flow is stable. Stable. Good. So what I'm going to do is just implement that little program right here in the Navier-Stokes. Easy to talk about, hard to do. And we're just going to plug those in there and throw away nonlinear terms. And similar to what we did with the waves, with the sound waves, similar but not quite. Also, let P equal P0 of R plus P1 of R and T, because we're looking for the full time dependence. So yeah, let's see. When you go in to this differential equation with this expression here, you get dv1 dt, because there's no explicit time dependence for the v0, plus v0 plus v1 dot grad v0 plus v1. So we're going to have to work that out. Equals minus 1 over rho gradient p0 minus 1 over rho gradient p1 plus nu del squared v0 plus nu del squared v1. Okay. So this one we're going to work out here. So we will get v0 dot grad v0 plus v0 dot grad v1 plus v1 dot grad v0 plus v1 dot grad v1. Okay, so that is this thing right here. And of these four, this one is second order small in v1. So that one is small, and we can ditch it. And I'm going to circle the ones that cancel against each other. So this is the original problem. This, and this. Okay. So this, and this are an equation, the circle ones, and what remains is dv1 dt. I'll try to write this one a little neater. Plus v0 dot grad v1 plus v1 dot grad v0 equals minus 1 over rho gradient p1 plus nu L squared v1. So there's your linearized differential equation that you would have to solve. There are other schemes, but this is principally what has to be done, okay? That you would have to solve in order to solve this, to answer this question. The way it's answered is the following. So to solve, let's call this star. To solve star, what we do is we let v1 of x, y, z, and t, here, that's a little too big, let's just write it of r and t. Let v1 of r and t equal v1 of r, new name, but times e to the minus I omega t, or some exponential, okay? Minus I omega is fully general. When you do that, this turns into a sort of eigenvalue problem for omega, okay? So that's the trial solution, solve, and obtain omega equals the real part of omega plus I times the imaginary part of omega. And here's the whole thing now. If you obtain this omega, if you obtain it and you plug in here minus I times I as plus, so if the imaginary part of this omega that you find is positive, then this whole solution explodes and you have instability. So really that's the standard linear stability analysis schema. If imaginary part of omega greater than 0, then unstable. So it looks like we have a schema going here. Remember, you can see why, because this is then going to grow without bounds. So what's the problem here? To return to everything we've talked about, the schema is well defined. It's been implemented in a couple of simple cases, but the interesting cases, for example, the flow around an obstacle, this V0 hasn't even been found, okay? So this equation presupposes that you know V0. If you know V0, V1 is your unknown. Haven't even found the V0, so it's very, very difficult to pull this off analytically. Nonetheless, it is a very standard linear stability analysis. You can find whole books that have tackled various and assorted problems here. Good. I'm just going to end with a little list. Yeah. Little list of images. I've written down a couple of images. I think I have them on the board already. Let's see. Yeah, I'll just reiterate in case they didn't have them all there. So we'll just call this homework with red. So yeah, for your last set of notes that you turn in, we want some images, and screenshots, want to print them out, and again, just pictures of them just the way you do for your notes usually. We've got the von Karman, potential flow. Past a cylinder. Okay, a very standard thing. And the von Karman vortex street goes really well with that. So von Karman vortex street. And what else? Yeah. The Raleigh-Benard convection. There's a whole industry around that. That's basically the heating a layer of fluid and then convection currents arise, okay, in the fluid, okay. Maybe you find a good image of that. That's a classic problem as well. We of course didn't get there. Can't do everything in a short class like this, but it's part of this theme here. So that would be nice to look at. And if you can find the Kelvin Helmholtz instability. Like I said, we're just looking for images, so you should be able to find something pretty quick. Kelvin Helmholtz instability. Add a couple of those. These are the most important though, because we've talked about them at some length. This would just be for good measure. Okay, good. That'll be it, actually. That was our short introduction to fluid mechanics. Hope we get a chance to talk about it some more.